So now that we have some basic idea about what a Markov random field is and how we tend to represent the microstructure in different ways, whether it is in form of a microstructure graph or in form of two-point statistics, we can now move into the next part of describing microstructures, which we are going to do using a convolutional neural network. So if you look at this convolutional neural network, basically what we mean by this term convolution over here is that it is a mathematical way in which we are going to combine two signals, or you can think of two signals as the intensities to form a third signal which has its own intensity, right? So in that sense, you can think of this term convolutional as something which is referring to a form or shape which is going to be folded into curved or tortuous type of windings. So convolutional neural networks are used quite commonly for doing image classification and image recognition, and this is becoming a really important tool wherever you have got some sort of spatial dependence or spatial correlations between the data. So microstructure is a classic example where you have spatial correlations of different phases within your microstructure. And so that's why we use convolutional neural networks when we try and describe the microstructures. So for example, if you look at this microstructure over here, the question that you should ask yourself is, do you actually start recognizing or sensing some form of a spatial dependence of the pixels? So for example, if you look at the pixels over here, so you can start seeing that I have basically identified certain pixels from different regions of the microstructure. And then if I again look at a second set of pixels, so let's say I'm identifying that with the green ones. Okay, so now do you start seeing whether there is some form of a correlation between the red and the green? So that is basically the type of work which the convolutional neural networks are going to look at, and they are trying to capture this type of pattern dependencies in the microstructures. So once we are actually getting ourselves into a situation where we can classify the features in the microstructures, we can generate the digital microstructures, and we can actually start creating the digital twin of a material itself. Now, if you think in terms of looking at images using traditional neural networks, we can do that with an example of the same image that we were just looking at. So essentially what we are going to do is we want to think in terms of breaking down the image into different constituent parts. So what I've basically done is I've simply laid different segments of the image side by side in order to create what we would call a feature vector in case of your traditional machine learning or traditional neural network type of approach. And it so happens that this image is 530 pixels. This is basically what I measured out. This image is 530 pixels in terms of the height, and then 662 pixels in terms of the length. And so what that means is, if I'm thinking of this individual bit of image as a feature, I will have a total of 350,860 features. So now think in terms of what a traditional neural network would do. These features are going to be associated with the input layer. So that means I'm going to have at least a bare minimum of 350,860 nodes in my input layer. And then let us say that I have a couple of hidden layers and I'm not making it a very deep neural network. And if my input nodes are 350,860, maybe the first hidden layer I'll put 1,000 nodes, maybe in the second hidden layer I might have 10 nodes, and then in my output layer, again, I have got 10,000 nodes. So basically what I'm doing is I'm trying to take a microstructure which is represented by this many number of features and generating an output which is characterized by this many number of nodes. An output microstructure which is characterized by this many number of nodes. So when you are doing a neural network type of fitting, you will be having weights, and you will associate it with each of these interlinks between the nodes of one layer and the nodes of the other layer. So there is going to be a good number of weights associated with each of the layers. And then what you will understand is when you are dealing with a neural network with so many different weights, this neural network is going to become extremely heavy from a computational perspective. And so the main challenge that one faces in case of microstructural informatics is how do we cut down? So how do we actually translate a problem which in a traditional manner would be extremely computationally heavy to something which is much lighter in a computational sense. So this is where this use of convolutional neural networks becomes useful. So now if you think in terms of convolutional neural network, essentially what we are trying to do is the first thing we are trying to do here is we are trying to detect the edges of different features in the microstructure. So how do you actually think of an edge when you're looking at an image? You think of an edge in terms of a region where you have a very sharp change in the intensity value as you are moving across a certain pixel. So in that sense, this pixels becomes like a differentiator of one face and the another face. Okay. So edge detection means you are going to essentially compute a gradient, this gradient of intensity. And then why this becomes important is when you are considering the image, you are considering the image as a two-dimensional network of intensity values. So how do you actually do the edge detection? The first thing is you will need to create a kernel or a filter. And this kernel or a filter, whatever you choose to call it, this is basically a matrix. Remember, when we are talking about a microstructure, we are talking about a 2D array, and therefore, in principle, we are talking about a fairly large matrix. So when we are doing a convolution, we are actually applying a kernel, which is a much smaller matrix, and we are applying that kernel to every region of the microstructure, as you can see in this animation over here. So what do I really mean by it? So what I mean by it is, I'm simply going, when I say I'm going to apply the kernel over here, I will design the kernel in such a way that if I, let us say, take some sort of a mathematical relation between this part of the microstructure and this kernel, it is going to give me a drastically different value if this part is corresponding to an edge. So this is how one would actually look at designing the appropriate kernel. Now, as you apply the kernel over the microstructure, you will end up getting the convolved feature. So in case of image analysis, what we mean by a convolved feature is that when you apply filter using a convolution, essentially when you are applying the filter over the entire microstructure with a matrix which is designed in order to highlight certain patterns. So those patterns in case of a microstructure could be a grain boundary, it could be some form of maybe a microstructural defect or some orientation of different phases. So as this convolutional kernel is, as we are doing the convolution, the kernel is going to basically slide across the microstructural images, and it is going to compute the weighted sums of the pixel neighborhoods. So in this particular case, when I am translating this filter across the entire microstructure, you will notice that when I am going in the x direction, this filter can move once, twice, or thrice. So that's why in this convolved feature is going to have 3 units in the direction, the x direction. Similarly, as I am coming down, I can move this once, twice, and thrice. So again, I have got 3 units as I come down. So what do these values actually mean? So what I'm doing is, as I'm sliding this filter over the microstructure, I'm simply trying to create or find out this matrix sums, and then I'm simply writing out those values. right? And that is how I am finding my convolved feature. So essentially what we are getting now is some sort of a feature map, and this feature map is going to emphasize certain structural characteristics. So how do I in fact do a proper differentiation so that I can detect the edges? So this is where I use something known as a Sobel operator. So the Sobel operator is one of the classic edge detection filters. So this is really going back to what I'm having as my kernel or a filter over here. So Sobel operator is a very well established edge detection filters, and the Sobel operator basically has two different kernels. So there's a first kernel which is GX, and GX is defined in this manner, and then the second kernel is GY, and GY is defined in this manner. And the role of GX is when I'm translating this filter in the X direction, it is able to change, it is able to detect the vertical edges, whereas when I'm translating in the other direction, I'm able to capture the horizontal edges. So by and large, I have one kernel which is looking at the edges which come about vertically, and then I have another kernel which is looking at the edges which comes about horizontally. So once you have applied GX and GY to the microstructure, you can go ahead and get your final convolved features. Now, after you have done this initial convolution, the next part is to do a pooling. So what do we mean by pooling? By pooling, we mean that we are summarizing or we are compressing the convolved features by reducing the spatial resolution while keeping the most important information intact. So when you think about your microstructure, it is a fairly large matrix. So it could be something like 512 by 380 or something like that. And when you're applying the Sobel filter, it is still a 3 by 3 matrix, right? So after applying the Sobel filter, your convolved feature that you are getting at the end of it is only very slightly smaller than the microstructure size. And so what that basically means is you still have very large number of features that describe your output image at this particular stage. So what we really want to do is we have to come up with a way in which we can decrease the spatial resolution so that the number of features are going to reduce, but at the same time, we want to keep the most important structural information available over there. So how does pooling really work? So when we are talking about pooling, think that your feature map is being divided into small non-overlapping regions. So you can see in this image over here that I am considering these four parts, and these four parts are not overlapping with each other. So think of your feature map as basically non-overlapping regions, and then after that you will apply your pooling operation. So when you are applying the pooling operation, you could apply it in different ways. So you can do a max pooling. So max pooling means it is going to take the maximum values, and you want to use max pooling where you want to maybe highlight some of the very prominent features. So it could be like you want to find what the sharpest edge is. So in situations like that, max pooling works out really well. A different way of doing pooling would be to do an average pooling. So when you are doing the average pooling, instead of taking the maximum value in this region, you are basically taking the mean. So when you take the mean, what you are essentially doing is you are starting to eliminate the noise while maintaining a more or less average texture. And then other than max pooling or average pooling, you can do a min pooling. You could do a sum pooling. A sum pooling is going to add up the intensity values in the regions. So this is something which is going to preserve the total intensity of the features. So if you do a sum pooling, you will end up with a smaller and condensed version of the feature map. So in that sense, when you are doing pooling of convolved features, you are essentially looking at a process of downsampling the feature maps. And you can do this by taking doing max pooling, average pooling, min pooling, or sum pooling, so that your essential microstructural patterns, at least the ones that you want to capture, are retained while at the same time ensuring that your spatial resolution has gone down, and therefore the overall number of features required to describe your microstructure has also gone down. So after going over these concepts, now we can start looking at this entire convolutional neural network computational pipeline altogether. So if you think about your convolutional neural network, it is basically a deep learning model. And this type of deep learning model is designed to work with grid-like data. So grid-like data means images predominantly, or a microstructure in our case. And so what we are doing in this type of computational pipeline is that instead of looking at every pixel individually, we are trying to automatically learn patterns which are there in this image, and these patterns could be in form of maybe grain boundaries, it could be in form of texture, it could be in form of the shape of the grain layer by layer. So this is the overall idea of the convolutional neural network. Now, if you think about the convolutional neural network, you can divide it into different sections. So let us first talk about our input. So this input image is basically a microstructure, and let's just say it's a 2D microstructure. And here, every pixel in this microstructure is going to contain some information about your material. So that information could be in terms of the phases present, it could be in terms of the intensity, it could be in terms of the texture. And before you actually use the input image, you would want to pre-process it properly. So this is basically what we have talked about earlier, that you have to do some sort of denoising before you feed it into the convolutional neural network. Now, the convolutional layers themselves are the ones that we just talked about, that basically you are applying the kernels or filters like the Sobel filter over the image when you are looking at this convolutional layers in order to extract local patterns such as edges, grain boundaries, maybe a pore, whatever it is. So each time you do a convolution, it is going to produce a feature map which highlights this morphological characteristics. And essentially what you do is you will do a convolution, you will do a pooling, right? So your successive convolution is going to reduce the spatial resolution of the image progressively, while hopefully maintaining all the features that you want to capture. And then as you do the pooling over here, this pooling is also going to preserve the essential features while progressively discarding the noise. So this pooling and convolution is going to go on over here, and then after that, what you will have is a set of reduced feature vectors. Essentially, you can think that you have flattened out the image now, and from the image you have now gone to the feature vector, and this feature vector is representing the essential microstructural patterns in a very compact form. And now we have something which is ready to be processed by the actual neural network, which comes at the end. So this neural network is going to take this feature vector as the input, and it's going to work just like any other neural network that we have already discussed earlier in this course during the lectures that were taught by Professor Viswas. So now let us take a look at an example of what we can really expect when we use semantic segmentation and when we use convolutional neural networks with some commonplace thing in materials. So let's talk in terms of a green body where you've got a bunch of powders in there. So using this type of image processing, one can start detecting the objects and one can do a semantic segmentation. Remember, as we had discussed, the semantic segmentation simply classifies the pixel. So here, the semantic segmentation is classifying everything into whether that pixel belongs to a powder or whether that pixel belongs to the gap between the powders. So by doing this type of semantic segmentation, you place all of the powders in one class and all of the gaps or the pores in the other class, and therefore you get an idea about the porosity of the. So just to summarize what we have covered in this lecture, we have talked about the basic idea of image processing and how two-point correlation can provide useful structural descriptions for machine learning models. Then we looked into using this Markov random field type of approach for looking at reconstruction of the microstructures while maintaining the general distribution of the phases as it is. And then we also looked into the basic idea of convolutional neural networks. So the take-home message here for you is that there can be multiple ways in which one can digitally represent the microstructures. But regardless of how you represent the microstructure, you will come into a common set of problems. The first problem is if you featureize the entire microstructure, you will have a large number of features and you have to find ways of reducing the number of features. So one way we had talked about this was when you are doing two-point spatial correlations, it can be followed up with principal component analysis. That is one way of reducing the features. We can also use this idea of convolutional layers where we progressively flatten the image while at the same time maintaining key features like the edges or boundaries. So that would be a second way in which we can first, flatten the image, get to a point where the number of features is very small, and then after that you can do the two-point statistics. So that is another thing we talked about. And then the third thing that we have discussed is this idea of Markov random field. The Markov random field is going to be really useful if you have a sparse data set and you want to expand your overall data set size, because by using Markov random fields, you can recreate similar microstructures. So in a nutshell, these are the three key aspects that I wanted to touch upon when we discuss microstructural informatics. And with that, we will stop here for today. Thank you very much for joining.